This video is about why there are 8 flavours of gluons and not 9. Well, hopefully you have some understanding of gluons, or you've met the idea of gluons before, so that I'm not going to have to explain everything from scratch. But to keep it short, hadrons contain quarks, which some people pronounce quarks. Hadrons, you can have baryons with 3 quarks, and mesons with a quark and an antiquark. And there's a force that stops those hadrons from blasting apart, from exploding, holding them all together. That force is the strong nuclear force. And now between hadrons, the strong nuclear force is mediated by pions. It's the residual strong nuclear force. But within those hadrons, within a baryon, within, for example, a proton and a neutron, there are gluons that hold those things together. Those hold those quarks together in a single particle. And I explain all of this in my video series about the history of the Standard Model of particle physics. You can watch that yourself. But something that often comes up with students is, well, why are there 8 gluons and not 9 gluons? If you look at the list, we tell them that gluons, unlike quarks, which have 1 colour charge, gluons carry 2 colour charges. One is a colour charge and one is an anti-colour charge. So gluons can be red, anti-red, red, anti-blue, and so on. Their colour charges, red, blue, and green. That's just what we call them. And the reason why baryons hold together, if you look at a baryon, there'll be one of the quarks is red, one is blue, one is green. They're colour charges, not actual colours. And so we say that's colour neutral, or white, it's colour neutral, and that's fine. But the colour's constantly changing. And within that hadron, maybe a baryon, the colours are constantly changing between the different quarks. And the gluon is the particle that is doing that changing of those colours. This is part of the topic called quantum chromodynamics. Okay, fine. Well, if I look at every possible combination of colour and anti-colour, I get 9. So where do the 8 come from? And your first port of call is possibly Wikipedia, and that will baffle you. And your second port of call might be ChatGPT, and that will baffle you. So this video is not for people who are master's students of physics, or they're doing PhDs and they're thinking to themselves, well, why are there 8 colours of gluon? That's not what this video is for. This video is for A-level students and below who have an interest in particle physics, a little itch they want to scratch in their mind. Why are there 8 gluons and not 9? The short answer is, I don't know. And the short answer is, I can't figure it out. But I'm going to go for a longer answer, which might satisfy some of the curiosity of those A-level students, and those A-level students, when they get to university, well, they can ask then. My master's was in photonics, not in particle physics. We don't really go into this level of particle physics in the early part of an undergraduate degree in physics. It's really when you start specialising, and I didn't specialise in this. So the short answer is I don't know. But anyway, let's see if I can give you something of an explanation that hopefully will do something to inspire you. Let's start with this picture, and we're going to see a lot of this sort of picture. This is a quark at the top, this is a quark down here, and this is a quark down here. Or quark if you prefer, which I don't. This quark at the top is coloured red, this is coloured blue, this is coloured green. And I don't know what this baryon is. This could be a proton, a neutron, a delta 2 plus, a sigma 0. It doesn't matter. Whatever this baryon is, it has 3 quarks, and those 3 quarks have 3 different colour charges. Now let's just take this one example here, this top arrow. The red quark can lose its redness, and it can also lose its anti-blueness. Now if you lose anti-blue, that's the same as gaining blue. Now, if we look at this quark, again, still following the top arrow, it can gain redness and it can gain anti-blueness. And it currently is blue. So if this quark gains anti-blueness, the blue and the anti-blue cancel. And it also gains redness. So following this top arrow, The red quark becomes blue, the blue quark becomes red, and we have the picture on the right. But that process can happen with a single exchange of colour if we go the other way. A blue quark can lose its blueness, but also lose its anti-redness. And so a blue quark losing its blueness stops being blue, but losing anti-redness is the same as gaining redness, so the blue quark will become red. And up here, this red quark is going to gain blueness and gain anti-redness. So red gaining anti-red, that cancels the red, and we're left with blue, which also swaps those two quarks on the right around. So that is one, or a pair of processes that can happen to swap the red and the blue quark colours around. We also have the same sort of process happening between the red and the green quark. So the red quark can lose redness and lose anti-greenness, thus becoming green. And the green quark can gain redness and also gain anti-greenness, so the green and the anti-green cancel and we're left with red. Or we can follow the other process. The green quark can lose its greenness and also lose its anti-redness, thus becoming red. And the red quark can gain its anti-redness, which cancels the red, and also gain greenness, thus becoming green. So these are two processes as well. And we have the two processes between the green and the blue quark. And it's the same thing, but for completeness, I will say it out loud. The blue quark can lose its blueness and lose its anti-greenness, thus becoming green. The green quark can gain anti-greenness and also gain blueness, thus becoming blue. Or we can follow the other procedure. The green quark can lose greenness and lose anti-blueness to become blue. And the blue quark can gain anti-blueness, cancelling out the blue, and gain greenness to become green. So there we go. You look at that list and you think, that looks like 6 of the 8 gluons done. We can see what's happening. We're switching the quark colours around. There are 6 arrows there. There are 6 labels that indicate quarks. Fine. So that is 6 gluons. Well, not really. That's actually 3 of the gluons, not 6 of them. Each of these processes is a gluon state. And so this is one state, this is another state, this is another state. Now the fact that the process can happen in both ways, and there's a probability of each of those happening, it's still the same process, the swapping of the red and the blue in the top case, with a single exchange of an mediating particle. And in the second case, the swapping of the red and the green colour with the exchange of a single mediating particle. And so on. And don't forget Feynman's interpretation of antimatter, and so maybe that's how we can interpret anti-colour and all these arrows. But we don't need to go into that at this stage, thank goodness. So there are actually only 3 gluons. So where are the other 5? Well, let's have a look at this process. We've got 2 examples here. These are fun. We could have a red quark, which loses its redness and loses its anti-greenness to become green. Now, when that happens, where's this exchange going to? It just seems to be going to nowhere. Well, no, there's a vertex here. So whatever this change is, what's happening with this change, it's actually being split into 2 changes. And if you look here, we've still got the red from the first change. That's here. We've still got the anti-green from the first change. That is there. But we also have a blue and an anti-blue. So we've created as much blue as anti-blue in this process. Well, that's fine, because blue anti-blue is colour neutral, so we can do that. So there's a vertex, a particle vertex, or whatever you want to call it, in the middle. And this red anti-green kind of splits into a blue anti-green and a red anti-blue. And that's fine. Now, you might look at this picture here and say, well, hang on a minute, we've got 2 green quarks. You can't have 2 green quarks. Well, let's just be careful. Let's have a look at the colours that we've got inside this baryon. We've got one green, another green, and an anti-green. So the anti-green and the green cancel. We've actually only got one green in this particle right now. And what else have we got? We've got one red, we've got two blues, and an anti-blue. Well, that cancels one of the blues, so we've only got one blue. So actually we've got one green, one blue, and one red in that particle, this hadron, this baryon. But this baryon contains not just 3 quarks, but 3 quarks and whatever these arrows represent. Well, they're not really gluons, or maybe they are gluons. It's complicated. So we've got this this exchange happening. So what happens? The green gains anti-green, so that loses its greenness and gains blue, so it becomes blue. And the blue gains anti-blue, so it loses its blueness and gains red, so it becomes red. Now, if you look at the before and after picture, the red quark has moved round here clockwise, the blue quark has moved round clockwise, and the green quark has moved round clockwise. So there are 2 stages here. The red anti-green coming out of the red, but then splitting into 2 other processes, and those 2 together cause all of the quark colours to rotate around. Now, that could also happen if the green emits a green anti... Now, I need to think about which way around this goes. Maybe I should pause the video while I'm thinking. No, I won't pause the video while I'm thinking. I've got it later on in the video, so maybe I should just carry on. Well, let's zoom in and have a look what on earth I was thinking. Green anti-blue. There we are. So if this emits green anti-blue, it loses its greenness, and because it loses anti-blueness, it becomes blue, which is the same as what we've got here. Oh, I should just looked ahead. And then that one, that green anti-blue, can split by gaining red and anti-red. And the anti-red will cancel with this, and the red will come down here, and we'll end up with this. So it is possible to have this process where there are 2 stages, and the quarks rotate their colours in the way I've drawn it here, clockwise, with 3 different ways. The emission of red anti-green, the emission of green anti-blue, and the emission from this one of a blue anti-red. All 3 of those are going to cause the colours to rotate round. We've also got this other process down here, and if we just look at the start and finish, if the first one on this board, the one just sort of there-ish, we said that we're rotating those colours clockwise, well, the last one on this page, down at the bottom, we're rotating them anti-clockwise. So instead of emitting red anti-green, we emit red anti-blue, which splits, and we have as much green as anti-green produced in that split, and it's the same principle, and we end up down here. So if we look at this one in the middle, and you add up all the green, blue, and red, it's still colour neutral. It is. So, and just like we've got this red anti-blue here, we've got a green anti-red that could come out here and do the same thing, and a blue anti-green that comes out there and can do the same thing. One way you could try and draw it is to overlap them to show that the vertex in the middle, where this exchange happens, there it is. That's the vertex in the middle, but I'm not sure that actually makes it any clearer. So the top path, there are 3 different ways of getting that rotation of those colours of those quarks in the clockwise direction. And in the bottom path, there are 3 different ways of getting the colour rotation in the anti-clockwise direction. So, this is just to clear it up. Red goes to green, green goes to blue, blue goes to red. Or on the second one, red goes to blue, blue goes to green, green goes to red. So we've got those 2 processes as well. So is that 5 of the gluons? The first 3 that we talked about, although it looks quite difficult to pick out what's going on. Maybe I should draw circles around these hadrons. Nah, it doesn't matter, you can figure it out. So we've got process number 1, process number 2, process number 3. The 2 processes we just looked at, but I'm only showing 1, because if I try and draw them all on top of each other, it's going to get really messy. So what are the other 3? Well, I don't know, but let's just see if we can make some sense of this. What if we had a colour neutral gluon coming away from the red quark. And we could have, in order for it to interact, it's going to have redness as well as anti-redness. So the red quark loses its redness, but also loses its anti-redness, so it stays red. But where's that going? Well, that can't go directly to the blue quark, because there's no reason for... I mean, how would that work? How can the blue gain redness and gain anti-redness? I suppose it could. It doesn't. And we've got the green over here. You're going to have some red to lose redness. And you're going to have some sort of blue to gain anti-blueness. And that's not... There's no anti-blueness here, so that's not going to happen. But the red anti-red can split, it can change, it can modify, it can become either blue anti-blue or a green anti-green. Could do either, it doesn't matter because it's white. So the red anti-red, there's some vertex there where the gluon just changes colour from white to white, but it's a different white. It's now a blue anti-blue or a green anti-green. That's fine, not breaking any rules there. And then either of these two is going to gain the colour charge and the anti-colour charge of the other one. So if it's green anti-green that we've got, then we're going to gain a bit of blue and a bit of anti-blue and become blue anti-green, green anti-blue. If it's blue anti-blue we've got, then we're going to gain some green anti-green to get blue anti-green and green anti-blue. So it's the same. So whether the red anti-red splits into blue anti-blue or whether the red anti-red splits into the green anti-green, it doesn't matter. It's still going to produce blue anti-green, green anti-blue. And what does that do? Well, that switches the colour charges of these two quarks at the bottom. So it all started with this red quark. This red quark started it, but it didn't actually change colour. The red quark caused the other two quarks to switch colour. Is that one of the processes? Is that one of the what we'd call gluons? And of course we can look at the other example. So green quark emitting a green anti-green gluon. Splitting, becoming a red anti-red or a blue anti-blue, and then splitting and becoming like we have here and switching. So the green quark emits a colour neutral gluon and it causes the blue and the red quarks to switch colour. And we've got the same thing. Here's a third example. The blue quark emitting a blue anti-blue. So blue quark losing blueness but also losing anti-blueness. Thus it stays blue. But the blue anti-blue being itself colour neutral there's a vertex there which connects to either red anti-red, green anti-green, one of those two. And either one of those two is then going to split into green anti-red and red and red anti-green. And it switches the colour charge of these two. So the blue one started it, but it actually switched the colour charge of the red and the green. So are they the 8 gluons that we've got? Now, I don't know if this text is going to come out very clearly. It's probably not recording high definition. Hopefully it is, but it's probably not. So I'm not sure if you can read this text if it gets a bit small, but it's just what I've explained anyway. So if you want to pause it and try and zoom in and read it, you can do. I don't think there's that much new information here. In fact, let's zoom in. If I zoom in, then you can pause this and read that yourself later. Red quark loses red and loses anti-blue, same as gaining blue. It's everything I've already said there. The bit you might be interested in is what it says at the bottom here. For those last 3 processes, read it, see if it makes sense to you. I'm not sure it necessarily does. Well, you never know. It might do. It'd be nice if it does. Right, so those are 8 processes. 8 processes that happen. And we could even summarize them like this. The first process involves either a blue anti-red or a red anti-blue. The second one involves either a red anti-green or a green anti-red. The third one involves either a blue anti-green or a green anti-blue. The fourth one involves either a red anti-green splitting or a blue anti-red splitting or a green anti-blue splitting. The fifth one, I've lost count, red anti-blue splitting or blue anti-green splitting or green anti-red splitting. And the last 3 there, are colour-neutral gluons that are splitting to other colour-neutral gluons, and then, well, I don't know if you'd call that splitting even, and then splitting into other gluons that cause colour changes within the baryon. Now, all of these processes are going to be happening, so these colours are going to be constantly changing, which is why we call it dynamic, quantum chromodynamic. Quantum because there's only 3 possible colour states, red, blue, green, and of course for gluons the anti-colour states, and for anti-baryons and anti-quarks within the anti-baryons. So there's 3 colour states. That's a quantum number, 3 of them. So that's the quantum chromo. We use colour as the analogy, so quantum chromo, and dynamics because it's constantly changing. Now, if we go back to the list we originally had, of 9 what we thought might be gluons is there. And if we look through this list, we can see that we can match some of them up. So the red anti-red, that character appears down there on the 6th process that I've listed. What else have we got? Red anti-blue, that appears in 2 different places. What else have we got? Red anti-green appears in 2 different places, and so on. So you can go through here and you can see where these different combinations of colours and anti-colours, all of them appear somewhere on this board of 8 different processes. And I can't think of any other processes than these 8. The first 3 involve a straight swap. The last 3 involve a straight swap, but because of the 3rd one, and the middle 2 involve a rotation, so everybody shuffles. I can't think of any others, but there almost certainly is plenty of others. So that's what I've just summarised there. There almost certainly are other processes that I haven't thought of or that I haven't included. Almost certainly. I mean, you could argue, why do we go green anti-green and then red anti-red splitting? Why wouldn't it go green anti-green, turning into red anti-red, turning into blue anti-blue, and then splitting? And that would add an extra step to this particular chain here. Would that make any difference? Well, we'd end up with the same outcome. Would that mean it takes longer? I don't know. There's a lot of I don't knows here. But when you look up the different gluons, you find yourself getting confused, and you try and match up what is written. And you might come up with something like this. You might say, okay, well, this has a red anti-blue or a blue anti-red. Now, in probability, when we have or, what we do is we add 2 probabilities together. And there's a gluon listed as red anti-blue plus blue anti-red. And the divided by the square root of 2, that is just a way of normalizing the probability, so that if this process happens, it is one of these 2 that causes it. So that is a gluon. So in other words, this process is a gluon. Not the red anti-blue, blue anti-reds themselves, but the process. Well, maybe we should call it a gluon state. There are 8 gluon states rather than 8 gluons. And you can see that we've got red anti-green, green anti-red. We've got blue anti-green, green anti-blue. So far, that looks very sensible. How do you write the probabilities of these things happening? I don't know. I really don't know. I can't figure it out. I'm not clever enough. If we turn to the next one, the next bit here, you'll see that there were 2 processes, and of course this happens 3 times. There's 2 processes that have the same outcome. We had blue anti-green and green anti-blue interaction, directly switching these 2 quarks, the green and the blue. But we also switched the green and the blue by the emission of a colour-neutral gluon from the red. Are they 2 part of the same gluon state? Because they're the same start and finish line, but if that's the case, then there are really only 5 gluon states. The direct swaps, and then the rotations. There is not anything else we can do there. So you go on ChatGPT and try and read what it tells you, and it says the more exotic states are strengthening colour charge, whatever that means. I'm not sure it makes any sense, and I'm not sure I believe ChatGPT. So, are these actually 2 different processes, or are they the same process? Are these 2 different processes, the swapping of red and blue? Or are they the same process? Are these 2 different processes? Or are they the same process? I don't know. So this is what I've said here. People who are cleverer than me, and there's a lot of people much cleverer than me out there. People, perhaps they're studying in a third or even fourth year of their doing a master's in physics, and they're focusing on particle physics. I mean, when I was doing my degree, there were particles like the Higgs boson hadn't been isolated. That was when I was doing my degree. Z0 boson, that was only recently, relatively recently isolated. So there were, there's particle physics has moved on since I did my degree. But when I did my degree, I didn't study any of this. I don't know this stuff. But people who do, people who have devoted years of study to this, maybe they're doing PhDs on this sort of stuff, have said that there are 8 unique gluon states. And you cannot create any one of these unique states by combining any of the others. This is one set of 8, but there are other ways of formulating the sets of 8 states. And I suspect the first 6 don't really change. I suspect it's these bits down here, the last 2, that form a complete set, where instead of red anti-red minus blue anti-blue, maybe we have red anti-red minus green anti-green. Well, if we have that state, we probably have some differences to this one as well. So there's going to be different ways of formulating these 8 gluon states. But they all produce the same results, apparently, and there's no advantage to having different sets. They're no simpler than these, they're no more complicated than these, so we usually just say, here we go, these are the 8 states. Now, trying to match them up to the list of 8 we had before, I can't do it. I'm not clever enough, but maybe you can certainly try, and maybe you can get somewhere with that. A better explanation for why there are 8 states can be found if you have a look at things like Murray-Gell-Mann, or Gell-Mann, I don't know how you pronounce his name, I've always said Gell-Mann, how he formulated them, looking at matrices, transformation matrices. These are 8 unique transformation matrices. That's what they are. And we call them gluon states, but if you look, we're all very well as saying there are 8 unique gluons, but look, red anti-blue, where's red anti-green? There it is. Where's red anti-red? There it is. Where's blue anti-blue? Blue anti-green. Blue anti-red. There it is. We've got green anti-red. We've got green anti-blue. Green anti-green. All 9 of what we saw at the beginning are found in these 8 states. You'll see comments if you ask ChatGPT why there are only 8. It'll say, well, because there's no colourless state. There's no singlet state where it's the same colour charge as anti-colour charge. Fine. So what's going on down here then? Because that's what it looks like to me, although we're subtracting the probability of this from the probability of this, B anti-B subtracted from R anti-R, although these aren't really probabilities, they're sort of wave functions. And how do they relate to probabilities? Well, the square of the wave function is, well, let's just say it's the probability of a particle within some range of space. Let's leave it at that. Squaring a wave function is very strongly, well, it is a probability. A probability of what depends on the wave function. So, what was I saying? Oh yeah, so these things, R and anti-B, you can think of those as wave functions. So it's related to probability, but it's not exactly probability. I've said I don't know too many times in this video to count. So if you want to go in the comments section and call me an idiot, please go right ahead. Happy to be called an idiot for this, because let's face it, unless you are in your 3rd, 4th year of studying your masters in physics and specialising, doing specialist bits on particle physics, you might not do this. You don't do this stuff at the beginning of quantum physics. It's right near the end. And, yeah, I didn't get onto this when I was doing my degree, for whatever reason. It wasn't a bad degree. So if you want to call me an idiot, go ahead. Or what you could do is try to do a better job of explaining why there are 8 gluon states without simply saying, this is the challenge, because maths. Because these are ways of writing Murray-Gell-Mann's 8 unique matrices for transformations of the colour charges. I mean, that's true, but that's not very convincing for an A-level student, whereas something tangible like this is more convincing for an A-level student, but it's almost certainly not how it really is. You can't see what I'm looking at. It's almost certainly not how it really is. But, you know, hopefully you found that useful. Yes, get involved in the conversation in the comments. I'm desperate to hear what you think about this. I haven't seen any other videos that do a convincing job of explaining why there are 8, not 9 states, but trying to think about different transformations that can happen, I could only come up with 8, and that was, you know, same number, maybe it's related. Let me know what you think.